So again, welcome everyone to the Earth Systems and Climate Change Hub Science webinar series. Thanks all for your patience in just getting the screen sharing function sorted. As I said earlier, if you wouldn't mind muting once you arrive, if you're not already muted, just so that we have a little less feedback and distraction for our speaker. So please just mute if you haven't already muted. So today's science webinar will be provided by Dr. Harun Rashid, and Harun is a research scientist at the CSIRO Climate Science Centre in Melbourne, and his research interests cover the area of modelling climate variability and change, with a particular focus on improving the realism of climate models simulations through understanding the causes of the model's systematic errors. Harun is a lead chief investigator of the Earth Systems and Climate Change Hub project, Project 2.5, Improving Australia's Climate Models, which is Access. And today Harun will be talking on Australia's National Climate Model, Access, Development and Application. And I think you might have noticed that in the bottom panel of the Zoom webinar platform, there's the ability to press on the chat function, and we'd like to manage and facilitate the question and answering function of today's webinar via the chat box. So throughout the whole webinar, if you have any questions for Harun, please do write them in the chat box. And when we get to the end of Harun's presentation, I'll facilitate the question and answer. So I think that would be the easiest way to manage that. So I think I'll hand over to Harun now. Thanks.
Thanks, Sonia. Hi, everybody. My name is Harun Rashid. I'm a member of the Access Couple Climate Modeling team. And as Sonia said, I lead a NESP project, which is responsible for the development and development of Access model. So in today's talk, I'm going to talk about Access, its development and application. But before I do that, I would like to talk about the usefulness of having a good climate model. A good climate model is able to realistically simulate the past and present climate conditions. The models are considered the best tools to predict future climate. The climate change information is obviously vital for planning in various sectors like food security, food and water security, long-term infrastructure, a sustainable ecosystem. Climate change projections provide information to policymakers required for adaptation and mitigation. And we scientists use climate models to experiment to understand the causes of climate variability and change, including climate extremes such as droughts and floodings. So I structure today's talk in two parts. The first part is an overview of Access climate model and climate modeling in general. And I'll give some examples from of its application from a past version of the Access model. In the second part of the presentation, I'll talk about the development work that my colleagues have been doing as part of NESP 2.5. And I'll finish with a few concluding remarks. So this is a schematic representation of the Access climate model. You might have seen it elsewhere as well. So basically, Access has a number of components representing the different subsystems of the climate: atmosphere, ocean and sea ice, land surface and other terrestrial processes, and atmospheric chemistry and carbon. So all these component models representing these different components are coupled together through a software infrastructure called coupler to make the Access model. So this is a bit of a more detailed schematic of the processes in the climate system. So we all know that the climate system is mainly driven by the output from the sun, solar radiation. Much of it, some of this solar radiation, about 30%, is reflected back into the space, and the rest is absorbed by the Earth atmosphere system. This radiation does not fall equally on the Earth's surface. So because of this differential heating of the Earth's surface, atmospheric motions arise, and eventually also the oceanic motions. So these atmospheric motions give rise to motions are organized into different weather systems that we see in our everyday weather forecasts. And also some things that we don't see, but we can measure, the large scale atmospheric circulation systems. So a consequence of these motions is also convection, atmospheric convection, clouds, rainfall, which are pretty important climate parameters. In addition to this, there are a lot more other processes. For example, atmosphere and ocean interact, ocean and sea ice interact, and land surface and other elements of the climate system, they all interact. So all these processes and their mutual interactions have to be represented realistically in a climate model in order to have a good climate model. So, so to build a climate model, basically we have to first represent all these processes, dynamical and physical, and their mutual interactions as mathematical equations. Many of these equations are derived from the first principles of physics. Many others, especially which are relevant for very small scale, we have to parameterize them. A model is then constructed by representing the equations numerically on a finite three-dimensional grid, a schematic representation of which is shown on the right-hand side here. And when, so all the individual models, when complete, they are coupled together to build a complete Earth system model such as ACCESS. So the model can be then used to predict future climate. It does it by time marching, predicting future climate at a very short time later, of the order of 20 minutes, using an earlier snapshot of the climate. The predicted snapshot is then used to predict the next snapshot and so on. So doing this time marching, using this time marching approach, and given enough resources, we can we can integrate the climate model for as many years into the future as we like. But first, we have to convert the complex set of numerical equations into a computer program, and this is actually the ACCESS model, a huge computer program consisting of over 1 million lines of code. So here is a small sample of the computer code that is used to integrate the model in a computer. Obviously, for a big model, we need a big computer to integrate it. Just our desktop computers are not enough. So shown in this picture is the NCI supercomputer, Raijin. It has more than 84,000 cores, 128 GPUs, 300 terabytes of main memory, 8 petabytes of high performance storage capacity, 8 petabytes, that is 8 followed by about 15 zeros, and 37 petabytes of supporting project storage for big data. So we have this big climate model and then big computer. Then what can we do with this model? So as I mentioned briefly earlier, we can use this model to understand the nature and mechanisms of historical climate variability and change. We can also investigate the mechanisms of various climate variability modes. Some of the prominent modes are El Niño-Southern Oscillation, the Indian Ocean Dipole, the Southern Annular Mode. These are the main drivers of Australian climate. And to understand Australian climate and its variability, we need to actually understand the mechanisms and the nature of these modes as well. We can also study the climate change induced by external forcings, for example, due to changes in greenhouse gas, aerosol, land use, etc. ACCESS, a main purpose of building ACCESS is to contribute simulations to World Climate Research Program's couple model intercomparison projects. We did that for CMIP 5. 2 versions of the ACCESS model simulations were contributed in CMIP 5 a few years back. In addition to CMIP, the ACCESS atmospheric model is also used as a key component of the dynamical weather and seasonal prediction systems at the Bureau. And also some members of Australian universities, some researchers also use access model for their research. So as an example of use of access model, we show here the temperature simulation by the two access models contributed to CMIP 5, access 1.0 and access 1.3. And the simulation covers starting from 1850 to present and extending into the future up to 2100. As you can see, the two models simulate temperature and their simulations are pretty consistent. The figure in the inset here shows the same historical period, the climate simulations for the historical period, like up to 2016. But it also shows the corresponding temperature evolution from observation from this climate research unit temperature data. So what we can see is that over the historical period, two access climate models simulate global mean surface temperature, surface air temperature pretty well. Maybe there are some little differences there, but they are not supposed to exactly match with each other. So by looking at this match or consistency over the historical period, we try to get confidence for the future projections that the climate model gave us for our future planning. On the right-hand side, the two plots, the two panels here show the geographical distribution of the temperature change due to the high emission scenario, RCP 8.5, at the top for access 1.0 and at the bottom for access 1.3. So the both models show again temperature change pattern that are consistent with each other. For example, low temperature change or low warming over the ocean area, but higher temperature change over the land area, and more even higher temperature change in the northern hemisphere than in the southern hemisphere, especially over the northern polar region. So this plot shows similar plots as in the previous slide, but for precipitation. So global mean precipitation are again simulated pretty close to each other in the two models. And for future projections, access 1.3 projects a bit of a higher rainfall change compared to access 1.0. Again, there are some differences between the high emission and low emission scenario. The thicker curve shows the high emission scenario projection, and the thinner curve shows the lower emission scenario projection. On the right-hand side are the geographical distributions of this rainfall change from two models for the high emission scenario. On the top, we can see rainfall increases in, again, in the northern polar regions and also some places over the ocean. But over Australia and in the surrounding region, rainfall tends to be decreasing in the future. And this prediction is similar in both models, but access 1.3 predicts a bit of a higher drying over Australia and to north of it in the Eastern Indian Ocean. This is an example of the simulation of a prominent climate variability mode, namely El Niño-Southern Oscillation. The two top panels show the spatial structure of El Niño from observations, and the two bottom panels show the spatial structures from two access model simulations. As you can see, in the tropical Pacific, there's this high or warm temperature anomaly associated with El Niño, and this is pretty well simulated in the couple model, access climate model. One of the model shows the structure going a bit too far into the Pacific. This is a bias which is shown by very commonly shown by a lot of climate models. On the right-hand side are shown the power spectra for from two model simulations, and also compared with observations. So the black curves show power spectra of an El Nino index from observations, from two observations, the solid and dashed black lines. The red line in this plot shows the similar plot, power spectrum, from ESCC 1.0 simulation. So El Nino-Southern oscillation is known to have a periodicity around 4-year period, showing higher power between a time period band from 3 to 7-year period, shown by the two vertical lines here. So the model, although does not exactly match observation, but it actually does pretty well. And I should also say that from observations, if we consider a different observation period, then the structure of the power spectra actually differs slightly from the one that is shown here. So it is not expected that model and observed spectra will match exactly with each other. On the right-hand side plot is the power spectra from ESCC 1.3 compared with the same observations shown on the left-hand side plot. Again, ESCC 1.3 simulates the power spectral feature pretty well compared with observations. So this is a plot which compares ESCC models, two ESCC models, with all other global climate models submitted to CMIP 5 for a number of variables. So the couple models are plotted on the horizontal axis, and the different variables against which the simulation performance was measured are shown on the vertical axis. So at the bottom here, air temperature at 850 hectopascal, and then air windy speeds at upper troposphere and lower troposphere, geopotential height, surface air temperature, precipitation, and different components of atmospheric radiation. So different boxes show the performance of different models against the corresponding variable. So these different boxes are color shaded, has different color shadings. So the more blue a box has, the better the result is, the better the performance is. And orange and red colors are not good, meaning that for that particular variable, that particular model has low skill or low performance. So in a nutshell, the more blue that we see against a couple model, the better its performance is. So the best of the best is the multimodal mean, shown on the very left side here. So it has lots of blues in all the boxes, which is kind of well known now among the climate scientist community. Now the two ESCC models, not as good as the multimodal mean, but they actually show lots of blue colors, blue boxes, compared to many other climate models, for example, some of the models here. So from this figure, we can see that the two ESCC climate models actually rank pretty well among compared to the other CMIP 5 global climate models in terms of simulation performance. And this plot shows ESCC model performance compared with other CMIP 5 models over the Australian region, and a number of variables were considered to measure the performance: surface temperature, pressure, precipitation, climatology, and seasonal cycle, annual and seasonal cycle. So over the Australian region, ESCC 1.0 is actually ranked number 1, and the other ESCC model, ESCC 1.3, is also ranked very highly, better than average. So the ESCC models globally do well, very well, and over Australian region also do very, very well. So these are the performance from the past versions of the ESCC model. Now, so we are in the phase of, so over the last few years, we have been preparing the latest ESCC couple model for CMIP 6. So the CMIP 6, first I go into the access preparation, just a few words about CMIP 6. So CMIP 6 consists of a number of core simulations, MIP style simulations, pre-industrial control simulations, 1% per year CO2 increase, and abrupt 4 times CO2 run. And in addition to that, historical runs and a number of scenario MIPs. So the DAT runs and the historical run are, as well as the MIP runs are designed to answer a number of questions. For example, how does the Earth system respond to external forcing? And what are the consequences of various model and consequences and the origin of various systematic model biases? And how can we predict the future climate given strong internal variability and uncertainty in the forcing scenario? So these are the 3 main questions which are designed, so against which the experiments are designed to answer these questions in CMIP 6. So access for CMIP 6, as I mentioned earlier, access is a community effort between CSIRO, Bureau of Meteorology, Australian universities in partnership with the UK Met Office. And it has been, over the last 2-3 years, it has been funded by the National Environmental Science Program. And before that, previous versions of Access were supported by SCCSP. So Access CM2, the latest version of Access couple model, comprises an atmospheric model, which is based on the UK Met Office unified model. The ocean model is based on the GFDL MOM, and the CIS model is also from the States. And the land component is developed here in Australia, CSIRO, Australia cable system, and coupler is from Surfex in France. So we have another version of Access which has some more components like biogeochemistry, ocean and land biogeochemistry, and carbon cycle. And this is based on the couple model of a couple model version from CMIP 5, but on top of that, our system components have been implemented. And the aim is to contribute simulations from these 2 models to CMIP 6. So we have been going through various challenges, stop losses in recent years. So we have less FTEs to work on Access compared to we had for CMIP 5. CMIP 6, the scope of CMIP 6 is bigger than the scope of CMIP 5, more model outputs, more experiments, etc. And also model complexity has increased quite a lot. In one version of the model, for example, carbon cycle is included, and limited computational resources resulting in slow turnover in the development runs constitute some of these challenges. And also have in the way here is tight timeline, so delayed availability of forcing data, delayed release of atmospheric model component, which all have slowed down a bit the development of the latest Access model for CMIP 6. But CMIP 6 submission is a community service. We are only we are one of the only 2 Southern Hemisphere contributions. In the past, it was only we were the only one in CMIP 5. It is highly valuable, but can be all consuming because a lot of people have to work towards a timeline, bringing together resources from diverse sources, and they do not come on time, all of them. Impact on creativity when experiments need to follow protocol. So for CMIP 5, for CMIP 6, we are told to what sort of experiments, that's the point of it. So all climate modeling centers do the same experiments by different models. And then we have an ensemble of different climate model simulations using same forcing and data set and experimental protocol, but different climate models. And it can impact the staff career development as well. So we are aiming to do this DEC experiments as well as historical and some of the scenario MIP. After extensive testing and development, Access model is now almost ready to do the official CMIP-6 simulations. So there is not much result because it is still in the development mode, the model, but I show here some results from a development run of Access model. So what I show here is similar to what I previously shown for CMIP-5 version, the spatial structure of El Nino or ENSO. On the left-hand side is the pattern from observation, and on the right-hand side is the ENSO pattern from a development run. So we can see that there are lots of similarities between the two patterns, but there are also some differences, especially this westward extension into the Western Pacific, again, which, as I said before, is a common bias across various climate models. This plot shows the power spectra. The orange, the yellow curve here shows the power spectrum from a recent period, 1917, the past 100 years, 1917 to 2016, and the blue curve shows observational result from the past 100 years of the available data period, which is 1870 to 1969. And compared to this, these four curves show climate model simulated power spectra. So what we see is that the comparison is not, in terms of power spectrum, the comparison is not as good as the spatial structure at this stage. The model simulated ENSO is too periodic, and the period is too short, and also it has too much variance or too much power. So the Access model development team has been aware of this limitation. They have been doing various things to improve it, and this effort will continue in the future to improve this aspect of simulation. So now I move to atmospheric model development, which has been done under NESP Hub Project 2.5. Again, I would like to show with a schematic of the atmospheric processes. Some of the main processes are convection, cloud formation, aerosols, and chemical reactions between different atmospheric constituents. Some of them are injected into the atmosphere due to human activities, and also land surface. So under NESP, so in short, atmospheric model has numerous processes which have to be realistically simulated, but we do not actually attempt to do all of these things. We only focus on convection, cloud, and rainfall in this project of under NESP 2.5. So the problem is that rainfall is an important element of weather, but most climate models, including Access, show large rainfall biases in the tropics. Atmospheric convection is an important determinant of rainfall, so we have to look into it. And in NESP ESCC Hub Project 2.5, researchers are improving the convection scheme in order to reduce the rainfall bias in Access. So in the rest of this presentation, I'll show a few examples of my colleagues discovering important model errors and understanding their causes, modifying and or replacing the convection scheme to reduce the model error in rainfall, and examining the sensitivity of cloud feedbacks to model parameter changes. So this cloud feedbacks and its sensitivity to model parameter changes is important, because cloud feedbacks is the main contributor to climate sensitivity shown by various models, which means that under the same forcing into the future, different climate models project temperature change, which range over a over a range of values, temperature values from approximately 1.5 degrees to around 6 degrees. So this is an important thing to get right, because if we understand the reason for this wide range in temperature response into the future, then we can reduce this range, and reduction of this range is important in order to have a reliable climate projection into the future by climate models. So some of this work have been documented in various publications, which I list here. So in this plot, I show rainfall over the Maritime continent region. So here you can see various islands in the Maritime continent, Sumatra, Java, Borneo, New Guinea. So that area here. So this is a region of high rainfall and of very high convection, high deep convection, atmospheric convection. And this region not only has high rainfall, but it also affects other regions of the globe, weather in the other regions of the globe through something called atmospheric teleconnection. So it is important that a climate model gets rainfall simulation in this region right. But unfortunately, ACCESS and a lot of other climate models show large rainfall biases in this region. So in some of the work that we have been doing, we have been trying to understand the reason for this rainfall bias. So one thing we note here, so the top panel shows the annual mean rainfall in that area, and the other 4 panels shows the seasonal mean rainfall: December, January, February, March, April, May, June, July, August, September, October, November. So one thing we notice here is that over the large islands, so in New Guinea, Borneo, and Sumatra, higher rainfalls are located in this region. There are high rainfalls over the oceans as well, but over the islands, especially the big ones, there are even higher rainfalls. So this is something that we would like to simulate in the atmospheric model. Now in the center column here, I show similar results, but presented as a difference from observation for a version of the model, for the default version of the model. So the orange color here means that there is actually deficient rainfall, that is less than observed rainfall. And these deficient rainfall areas are mainly located over or around the island regions. Now, in order to understand the mechanisms of this rainfall deficiency or dry rainfall bias, we ran the same model, but with higher horizontal spatial resolution. And we saw that in the higher resolution model, the rainfall bias is a lot less than that from the default version of the model. The default version has a horizontal resolution of the order of 130 kilometers, the distance between the grid points, and the higher resolution model has a grid resolution of about 60 kilometers in the horizontal. So now that we have improved rainfall simulation in the higher resolution, we would like to understand what is causing this improvement. So the top panel here shows the difference between the higher resolution model, the so-called N216, and the lower resolution model, N96. And what we see here is that here in this blue color shows more rainfall. So we see more rainfall over and around the island regions. The bottom plot shows the difference between the orographic heights as represented in the 2 versions of the model. So again, we see that in the higher resolution version of the model, the orographic height is higher, or in other words, in the lower resolution model, the orographic height is lower. This is because of a technical reason. In the lower resolution model, the orographic heights have to be smoothed in order to avoid some instability. So, but a consequence is that the orographic heights of these islands are underrepresented in the low resolution model. And we then hypothesized that maybe this underrepresentation of the orographic height causes the dry rainfall bias in the lower resolution model. So we did an experiment to confirm this, to confirm this hypothesis. We took the same high resolution model, but then specified the lower orographic height of the lower resolution model. So high resolution model with the lower resolution model's orographic height, and then ran the simulation similar to the default version of the control version of the higher resolution model. And when we compare the rainfall simulation, we indeed see that in the higher resolution in the higher resolution model with lower or smooth orography, there is actually less rainfall simulated. So we can attribute some of the rainfall deficiency we saw in the lower resolution model is because of this underrepresentation of the orographic height. And this is actually over the islands, this accounts for, there is this underrepresentation of the orographic height represents about 50% of the rainfall difference or rainfall deficiency seen over the islands. So this is one piece of work which allowed us to understand the causes of some of the dry rainfall bias. So we have two avenues to improve this, either to use high resolution model, or if we have to use the low resolution model, we have to somehow parameterize the effect of this underrepresentation of the orographic heights to get the rainfall simulation right in this region. So next, I move to the work done by my colleague Hongyan Zhu, Dr. Hongyan Zhu from the Bureau of Meteorology and her collaborators. So she found a problem that in the atmospheric model, excess atmospheric model, the snow melting occurs at a single level, a single model level, which is around here about 5,000 meters, about 5 kilometers above the ground. So because the snow melting occurs at a single model level, the heat that is required to melt the snow is taken away from the model temperature. So it actually shows up as a cold spike at about 5 kilometers into the atmosphere. And this is unrealistic, and this can lead to actually other problems. So as a solution, what Hongyan and her collaborators did, they spread that snow melting over a range of levels so that it doesn't actually it doesn't occur at a particular level, at a single level, rather occurs over a range of levels, which corresponds to freezing level 2 or 3 degree Kelvin above this. And as a result of that modifications, the cold spike was reduced by about half. So what was the impact of this? What was the impact of this modification on atmospheric, on simulation of rainfall by the model? So the top panel here shows the original simulation. In this case, blue actually shows less rainfall or dry rainfall bias, and the red colors show excess rainfall. So we can see that over the Maritime continent, over the islands, there are large dry rainfall biases, as we saw in the previous slides. Now, with the modifications I have just described, the model was run again with those modifications. And what we see is that this is the difference plot. What we see is that over the Maritime continent, where originally there was less rainfall, there is now more rainfall. And over the oceans, where there were excessive rainfalls, there are now less rainfalls over the Southwest Pacific and also over the Western Tropical Indian Ocean. So this is a good thing for the model. It reduces, as a result of this modifications, the dry rainfall bias is reduced by simulating more rainfall, and the wide rainfall bias are reduced. The areas with wide rainfall bias are improved by simulating less rainfall. So what's the impact of the eastward propagation of convection? Now, a prominent observed feature of the tropical circulation is that the convective features propagate from west to east. These are well-known results, but in the original version of the model, what we see here, this is a plot longitude versus time lag. We see that this convection anomaly, as represented by the outgoing long wave radiation anomaly, which is a proxy for tropical convection, we see that the convection anomaly actually sits in just one longitude. There is no sign of propagation that is going eastward with time. But with those modifications that Hongyan did, the model now shows some eastward propagation of the convection anomaly, which is a definite improvement. This is another way of looking at that improvement, but this is now more relevant to a prominent tropical variability mode, the Madden-Julian Oscillation. This is an intraseasonal variability mode, and climate models normally get a hard time in simulating this mode. So in the original version of the model, so this is the wave number frequency spectrum. The colors show the power of interseasonal variance, and the power which corresponds to positive wave number shows eastward propagation, and the power or the shades which corresponds to negative wave numbers are westward propagation. So Madden-Julian oscillation is known to have a time period of around 50 to 60 day or 30 to 60 day, which corresponds to about 0.02 here, which is 50 day, and also a zonal wave number 1. So it has just one wave encircling the globe over the tropics. So that area here is shown by a little red box. We see that there is no peak of power. There is no spectral peak in that region there. But with the modifications that Hongyan did, we see that now there is more spectral interseasonal variance corresponding to wave number 1 and a time period of 40 to 60 day. So this is also a definite improvement as a result of the modifications that Hongyan and her collaborators did. So I now move to another example. So this is relating to an implementation of a new convection scheme in the excess atmospheric model. And this work is being done by Professor Christian Jacob at Monash University, and Dr. Rob Warren, in the same place. So the problem, first the problem. So the top panel here shows the time step simulation at the time step level of rainfall. And so these red curves, so what it shows is that at the time step level, the excess atmospheric model shows on-off behavior of rainfall. So at one time step, it could simulate, say, 6 millimeter per hour or even up to 15 millimeter per hour rainfall. And in the next time step, it can go to 0. Now, this is unrealistic. And in nature, rainfall doesn't behave like that way. So 20 minutes before 15 lot of rainfall, and 15 minutes later very small or 0 rainfall. So this again is a feature which is seen in many atmospheric models, and to address this problem, they are implementing a new stochastic multi-cloud model in the axis. And as a result of the implementation of this model, this on-off behavior at the time step level of the excess atmospheric model is much reduced. And still, the total rainfall, which is the sum of convective rainfall and large-scale rainfall, which is shown by the black curve here. So the black curve is the total model simulated rainfall at 3-hourly interval, and the dotted lines are the observed rainfall from an experiment in the northern Australia Darwin region. So the total rainfall compares well, but convective instability, the rainfall resulting from the convective instability is also much more realistic now. So the last example that I will give is from Rob Coleman and his collaborators at the Bureau of Meteorology. So this work addresses the sensitivity of cloud feedback, which is related to the spread in climate sensitivity seen in climate models. So what Rob has been doing is that using a version of the Access atmospheric model, they are changing a number of parameters in the cloud scheme, which are fine-tuned during the tuning process of the couple model. So the motivation for this work is to the best way to reduce the huge uncertainty of temperature projections, which I mentioned briefly earlier, and also determines the mitigation scale effort needed to meet policy critical targets, for example, Paris Agreement. So for example, how much greenhouse gas we need to reduce in order to keep the temperature increase within 2 degrees, as is required by the Paris Agreement. It also addresses among the largest biases and uncertainties in the Access model. So cloud feedbacks, as I mentioned earlier, is the largest contributor to the uncertainty in climate sensitivity. And some of these problems actually can come from the Southern Ocean clouds and Maritime continent, which I just described. So this plot here shows cloud feedbacks from all CME5 models, and the 2 Access models are shown in the red bar here. Access 1.0 is kind of in the middle and is closer to the average of the climate models. But the other Access model, Access 1.3, shows large cloud feedbacks, and in fact towards the higher end of the CME5 models. So in this work, 4 parameters have been changed, one at a time: liquid to water conversion, convective precipitation efficiency, ice fall speed, and treatment increase or decrease. And but the result is that important for confidence in model. So we want, because these parameters are tuned as part of the climate model tuning, we want to know whether cloud feedbacks are actually changed during this tuning process. Because cloud feedback is such an important quantity, we want to know if we inadvertently change that in the process of climate model tuning. Excuse me. So, so this plot here shows the result of the excuse me. So the top plot is the histogram cloud. In the vertical, it shows the cloud top pressure, and in the horizontal axis is the cloud fraction. So as a result of change in this parameter, liquid to water conversion rate, we see that there is some increase in the low and thick cloud. And the bottom plot shows the geographic distribution of this effect. So the low clouds, these are the typical regions of low cloud formation, and the low cloud, the radiation, the impact of this low cloud formation on the radiation is reduced. But the important thing is that despite this changes in the cloud simulation, there is the effect on the cloud feedback is small. And the result of the other 3 parameter changes are smaller, which are shown here on the 3 right-hand side pairs of plots. But the main conclusion is that despite the regional differences, these perturbations do not shift climate sensitivity due to cloud feedbacks significantly. So knowing this result gives confidence in the climate model performance, that the cloud feedback that we get is not the result of some artificial tuning, but this is actually intrinsically coming from the model physics and dynamics. So to finish the presentation, I'll just give a few concluding remarks. So Access equips Australia with a global modeling capability to better manage weather and climate impacts, including future risks and including the management of future risks and opportunities. Two Access models figured prominently in terms of performance among other climate models in the CMIP 5 benchmarking. Despite limited human and computing resources, a good effort has gone into preparing the latest Access model for CMIP 6 benchmarking. Global climate models are becoming progressively more complex with the implementation of more refined model physics and higher model resolutions, which is schematically shown in this right-hand side plot here. Individual models are getting better and better. There is more and more complex, and there are also more and more components or processes being represented in the climate models. So continuing support for model improvements will be needed in order to maintain a world-class Access model in future. So I will finish there. Thank you.
Great. Well, thanks very much, Harun, for your presentation today. It's really appreciated. Just a reminder to everyone, if you have any last-minute questions for Harun, just use the chat function at the bottom of the Zoom screen and quickly write them there. We do have one question so far, Harun, for you from Nick, and he says, thanks for presenting. Does the introduction of a stochastic component in the convection scheme mean that simulations won't be reproducible bit for bit, i.e. no two simulations will be the same?
So simulations are not actually, cannot be reproduced bit for bit for some other reasons as well. For example, the truncation of stored data. So this, although the stochastic climate model is stochastic in nature at the subgrid scale, but the statistics it produces for the whole grid box is pretty consistent. It doesn't mean that it exactly replicates, but this is an acceptable approach now for cloud scheme modeling. So yeah, I believe, yeah, I think what is more important is to actually improve the simulation rather than, and if you actually, in the random number generator, if you use the same seed, you can actually reproduce it. But I think the purpose here is not to actually reproduce the exact climate in different models, but statistically the more realistic climate.
Okay, thank you. And then another question from your colleagues here at CSIRO in Aspendale. Why is the Access 1.3 model cloud feedback different from the HadGem2 ES model cloud feedback, which was essentially the same model, the same cloud scheme? So
Access 1.3 had a different cloud scheme actually. In fact, Access 1.0 and Access and HadGem2, their CMIP 5 version of the Matterfist model, had the same cloud model, which is a diagnostic cloud model, but Access 1.3 used a cloud scheme, which is again from the Matterfist, but it is called a PC2 cloud scheme. So yeah, it's different from HadGem2, the CMIP 5 version of the HadGem2 model.
Yep. Okay. And Johnny asks, does Access plan to replace CICE with LIM in the long run, in line with the Met Office?
So CI's component, I think, yeah, I think it has been used and along with the MOM, the GFDL MOM Ocean model here in Aspendale, and we have a different coupling strategy. And I am not aware of any change of CI's model in line with the Matterfist model.
And one more from Dan, who says, when you say uncertainty, does that mean spread among model output values?
So uncertainty in projections. So different climate models can respond to the same forcing in a different way because because the different climate models are actually built in different ways. They have different parameterizations. And also climate models are the result of a highly nonlinear highly nonlinearly directing processes. So if there is a small change in the input, for example, or in the parameter, then it can lead to a different outcome. So different climate models are characterized by their own physical parameterization schemes, own numerics, some of the models are spectral, some of the models are grid point. So there are enough differences which can be amplified due to nonlinear interactions among the model components. So even though there is same level of forcing, it can actually result in, especially in the future, and also for the present simulation, different outcomes. Different outcomes means that, a temperature change of 6 degrees versus say 2 degrees at the end of this century.
Fantastic. Well, that's all the question that we have today, and we're about 1 minute right on time, so we might end it there. So thanks again, Harun, for a fantastic presentation. Really appreciate it. And just before we go, I'd like to just draw your attention to the next Earth Systems and Climate Change Science webinar that's coming up next month on the 16th of October. It'll be provided by Dr. Scott Power from the Bureau of Meteorology, and it will be around variability in climate extremes and a changing climate. So stay tuned for that, and a reminder about that webinar will be sent out shortly. So once again, thank you very much from the Earth Systems and Climate Change Hub for attending, and we hope to see you soon. Thank you.
All right, thank you.